Chapter 4 Atoms. Let's review real quick. Matter is anything that has mass and takes up space. All matter is made up of elements, which are substances that cannot be broken down. And elements are made up of atoms. The atom is the smallest unit of matter. And atoms are everywhere. They're in the air you breathe, the chair you're sitting on, and the clothes you're wearing. Section 1 is over atomic theory. Starting with Democritus in about 400 BC, he was an ancient Greek who theorized that matter could not be divided infinitely. At a certain point, you had to reach a smallest piece. He came up with the thought that that smallest piece of matter would be called something an atomos. That just means indivisible or can't be cut. And we turn that into atom. Since it was ancient Greece, he had no proof, and few people believed him. Fast forward to John Dalton. He lived from 1766 to 1844. He was an English chemist, physicist, and meteorologist. He's best known for introducing the atomic theory into chemistry and for his research into color blindness, which he also had. People were a little more accepting in the 1800s of his atomic theory because he did have evidence at the time. His theory states that all matter is made up of atoms, small solid spheres. We call this the billiard ball model. He also said that atoms are indivisible and indestructible, much like Democritus said, and that atoms of the same element are exactly alike. Atoms of different elements are different from each other. Compounds are formed by joining two or more atoms. Dalton's theory of atoms supported the law of definite proportions, which just says that a chemical compound is made up of the same percentage of elements. This means that elements combine is a whole number ratio when they react. Water's always made up of 2 parts hydrogen to 1 part oxygen, and that gives us H2O. And this is true for all chemical compounds. Next, we have Sir J.J. Thomson, who lived from 1856 to 1940. He was a British physicist credited in the 1890s with the discovery of the electron, the first subatomic particle to be discovered. He also found the first evidence that stable elements can exist as isotopes and invented one of the most powerful tools in analytical chemistry, the mass spectrometer. He conducted his experiments with cathode rays that showed atoms could be divided. His experiments showed negatively charged particles that came from inside the atom. These are electrons. A cathode ray has 2 metal plates at the end of a vacuum tube. The cathode has a negative charge, and the anode has a positive charge. When voltage is applied across the plates, a glowing beam comes from the cathode and strikes the anode. Since it's a vacuum tube, which is a tube with all the air vacuumed out, he could see that that beam came from the negative end of the cathode. This became J.J. Thomson's plum pudding model. So building from John Dalton's model, that we just had these tiny spheres that everything was made up of, Thomson gave us this plum pudding model. Since he successfully separated negative particles, but he couldn't separate the positive particles, he just proposed that the electrons are spread throughout the atom, much like blueberries in a muffin or chocolate chips in a cookie. Because he was British, they have what's called plum pudding, and that's why they call it the plum pudding model. Next, we have Ernest Rutherford. He lived from 1871 to 1937. He was a New Zealand physicist who came to be known as the father of nuclear physics. He found that the atom is mostly empty space and nearly all of the mass is concentrated into this tiny central nucleus. He did this using what are called the gold foil experiments. He fired positively charged particles at a sheet of gold foil. Most went through unaffected, but some bounced away. This suggested that the atom's positive charge was concentrated at the center of the atom. We now know this is the nucleus. Here's Rutherford's atomic model. He stated those electrons are scattered around the atom, but there's a lot of empty space between them and the nucleus. Compared to the atom, the nucleus is very small, much like a marble in the middle of a football field. Next, we have Niels Bohr. He lived from 1885 to 1962, and he was a Danish physicist. Bohr's greatest contribution to modern physics was the atomic model. The Bohr model shows the atom as a small, positively charged nucleus surrounded by orbiting electrons. His work earned him the Nobel Prize in Physics in 1922. Later, Bohr fled Denmark and ended up working on the Manhattan Project in the United States in 1943. Niels Bohr proposed that those electrons are arranged in these circular energy levels, much like planets orbiting the sun. When electrons will gain energy, they jump from a lower level to a higher, and a loss of energy causes them to fall from a higher level to a lower. And when this happens, they give off light. So we will look at later on the different colors that are emitted from different types of elements in our tubes. Next, we have Erwin Schrödinger and James Chadwick. Erwin Schrödinger lived from 1887 to 1961. He was an Austrian theoretical physicist who contributed to the wave theory of matter and other fundamentals of quantum mechanics. His model does not define the exact path of the electron, but predicts the location. That's what gives us this cloud. That's why we refer to it as the electron cloud theory. And then Sir James Chadwick lived from 1891 to 1974. He was an English physicist who was awarded the 1935 Nobel Prize in Physics for his discovery of the neutron in 1932. In 1941, Chadwick wrote the final draft of the Maud Report, which inspired the US government to begin serious atomic bomb research efforts. Chadwick is credited with discovering the neutron, which has no electrical charge and the same mass as the proton, which made it virtually undetectable until later on when technology could catch up. This is actually section 4.3, but it's so short and it just builds off of these scientists that we just talked about. So we're going to throw it in here. Dalton gave us that billiard ball model. Thomson had the plum pudding. We had positive and negative charges. So you had negatively charged particles that were spread throughout a positively charged pudding. Then Rutherford gave us this nucleus. Said this is positively charged, and all that electrons, they must just be floating around somewhere. Then Niels Bohr in 1913 gave us those energy levels. His work with wave theory said that those electrons work off of waves, and they have to be organized somehow around that nucleus. And this is the most common depiction that we use on our two-dimensional pictures of an atom. And then Schrödinger in 1926 had this electron cloud model. We know that those electrons are somewhere in this region, but we can't pinpoint them, much like you can't pinpoint a water droplet in the midst of a cloud. So today we know that atoms have a nucleus that has protons and neutrons, and there are electrons that orbit the nucleus, and they behave like waves on a string. We know that those electrons, their exact location can't be determined because they're too tiny and they're moving too fast.